Okay, so in the last video, we illustrated that if a function is differentiable at a, then it must also be continuous at a. However, if a function is continuous at a, doesn't mean that it's differentiable at a. And so illustrating this in a graphical manner, that if a function has a corner, then that function will not be differentiable at a. If a function has a discontinuity, then the function will not be differentiable at a. And also, if the function has a vertical tangent, then the function will not be differentiable at a. A vertical tangent is going to imply that the derivative evaluated at a is going to have a slope that is undefined. And this type of question makes good for conceptual theoretical check, right? A graph that has a corner, a graph that has a discontinuity, and a graph that has a vertical tangent is not differentiable at A. Now to finish, well, not to finish this section up, but there's quite a bit in this 2.2. So again, we haven't strayed. We're still in the 2.2. I'm just trying to break it up into segments of it. So we talked about the first derivative. Let's talk about the second derivative here. And so in this particular case, let me do a pause. Okay, so I wanted to recap, and I was cutting and pasting, so I'm not too sure where I will have to relocate this file. But if we're given an object that's moving along a line with a position function with respect to time, you might want to consider here linear motion, which means motion along a straight line, such as a piston moving up and down in a cylinder, or a race car moving along a straight track, or an object dropped from the top of a building and falling down, or a ball, thrown straight up, and then it's falling straight down along the same line. And so when you're thinking about the first derivative of this position function is going to be the velocity function. So the velocity is the rate of time. I misspoke. The velocity is the rate of change of position with respect to time. And another way to write the velocity function is equal to the first derivative of the position function, which is the same as saying ds over dt. You're taking the derivative of s with respect to t, and the units for the velocity is going to be distance per time. And so therefore, the sign of your velocity will indicate the direction of motion. So if your velocity is positive, then that's going to indicate that the object is rising. If the velocity is negative, then that's going to indicate that the object is falling. And if the velocity is 0, then the object is going to be standing still. And so in this case here, the speed is always the absolute value of velocity, meaning speed is always positive. And the speed describes the motion of an object or how fast it is going. So again, it's not taking in consideration if you're moving forward or backwards. And then the acceleration is going to be the rate at which your velocity changes. So look at this definition. So the definition of your velocity is the rate of change of your position with respect to time. Your acceleration is going to be the rate at which your velocity changes. And let's just be a little bit thorough that this is also going to be respect to time. And the acceleration will be, and it depends on how you want to write this. So either the acceleration is equal to the first derivative of your velocity, which is the derivative of your velocity with respect to time, and the units would be distance over time squared. Or another way of saying your acceleration function is going to equal to the second derivative of your position function. Or if we're using the Leibniz notation, d squared, so this is the second derivative of your position function with respect to time squared there. Oops. And then one other interesting fact is that if acceleration is greater than 0, it's going to indicate that your velocity is increasing. And if your acceleration is less than 0, then your velocity is going to be decreasing. So this is just a snippet of what I proposed on your handout that I gave you. Another thing that I want to talk about here is another reason why we use the first derivative. And we use the first derivative and the second derivative when it comes to the graphing component. So this is just conceptualized because we haven't talked about the derivative here, but what this is saying here, that if your first derivative is equal to 0, or your first derivative of x is equal to b undefined, then for those values of x, you have possible what are called critical values. So what is this illustrating here? So if you were graphing here on a number line, what does the first derivative represent? It represents the slope of a tangent line. And if the slope of the tangent line is equal to 0, then that's illustrating here that the tangent line will have a horizontal. So let's just say here you have some parabola. And let's just say at this given value C, at this point right here, your tangent will cross at that point, bear with me, and you will have a horizontal. And notice how your graph is concave down. But if you look at, let's say, the slopes here, aren't these slopes of these points here going to be positive, whereas these slopes here are going to be negative? So what this illustrates is that if f prime, which is the first derivative, changes from positive to negative at C, then you have which is called a relative maximum. However, if you take a look and you have a parabola that looks something like this, and you're focusing on this horizontal here, and notice that you have a horizontal here. So let's just call this C1, and then let's call this C2. Notice now what happens, that the slopes here now have negative slopes, but the slopes here have positive slopes. So now what this is saying, that if f prime, in this case, is going to say changes from, and now it's negative to positive at C2, we'll call this C1, then you have a relative minimum. Now, these particular concepts are coming from the 3.1. So I'm kind of squeezing in these concepts together so you will see the importance of why we're finding these first derivatives. This is giving us techniques that will assist us to find relative mins and relative maximum values. And those values are the y values. So what particular x value is going to produce a relative maximum value or a relative minimum? Now, on the other side, if you have, let's say, an undefined slope, so this will illustrate here something, you will take the cubic. So if you take a cubic here, now what's going to happen is that these slopes here, they're positive, 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 positive. Here, at this value of C, they're positive, 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 positive. This will be an example that a critical value will yield an undefined slope. And because there is no sign change in the first derivative, therefore that critical value will not have a relative minimum or a relative maximum. So when you set your derivatives equal to 0, and we'll do that later, and you set your derivative equal to undefined, those values are potential critical values. So just because you get some values doesn't mean that they're going to be critical. Those critical values are going to yield a relative min or max. It is the fact that we have to test the first derivative to see if there's that sign change. And that's what's coming on the horizon. But the reason why they wait is because there's so many different rules of the derivatives. And I'm trying to squeeze that technique in so that it's not too overwhelming when we get there to kind of start putting all these pieces together.